I want to take a look at the range formula. So what we're talking about here, let's look at a graph. So we launched some projectile at some angle, velocity v naught, some angle theta, right? And we launch it from the ground and it goes, in some sort of parabolic motion and ends up so far down the road, okay? The range, it's like the range of a medieval cannon, is the horizontal distance it can travel. Okay, and so for right now, let's focus on it being a ground-to-ground thing. So eventually we're going to get this formula that relates the range to these two quantities. We're not really interested in the height. We're not really even interested in the time it takes. We just want to know if we have something that we can launch at a certain speed v naught and what angle we use, those two things are going to determine how far something goes. Okay, the range equation that always works, no matter whether it's a symmetrical case or whether it's not a symmetrical case, is just our standard horizontal position function. Remember, v naught cosine theta, that quantity is just the horizontal velocity. And the horizontal velocity is not a function of time. It's always the same, right? When we're talking about projectile motion, we don't have any drag forces. So the only force we're under the influences is gravity. Gravity always pulls us down, and so the horizontal component does not change. And so this is easy as distance equals rate times time. The horizontal distance you travel is just the horizontal speed times how long you're in the air for. So if you want to know your position at any moment in time, you just use this. If you want to know the maximum x, well then the time you use is just the total flight time. Okay, so if we use this, we can think about some things. Okay, so what did we just say in that? Let's use the fact that we know we're in a symmetrical case. I'm going to call this T max. That's the time we're at max height. And let's call this T flight. That's the entire flight time. And as long as we have symmetry, then T flight is indeed twice the T max. Right? If it takes us 2 seconds to get to max height, it takes us another 2 seconds to fall. So we know this relationship. And again, this is only true under symmetrical cases. Symmetrical cases meaning ground to ground, or you're on a building and you're shooting to a height of another building, right? Initial and final heights are the same. And so what else do we know? Well, we also know that at maximum height, our vertical velocity is equal to 0. Okay, well, let's take a look at that. Let's look at our vertical velocity equation. We know vertically we're launched at v naught sine theta, and if we're under the influence of gravity, we're going to experience a 9.8 meters per second squared acceleration for a certain amount of time. And if we look specifically at max height, that's when the vertical velocity is 0. So let's put a 0 in here and solve this equation. That would be the T max, right? At the T max time, we know that this is 0. And so if we solve for T max, that's just adding this and dividing by g. So then T max can equal v naught sine theta over g. But then we know then the flight time is just double that. So then we know that the entire flight is going to be 2 v naught sine theta over g. And again, if it takes 2 seconds to go up, it takes 2 seconds to go down. And remember, this is our vertical velocity. Like if we were launched at 20 meters per second vertically, it's going to take us 2 seconds to slow down because that's what g does. It takes away, in this case, 9.8 meters per second every second. Okay, so now we have the flight time in terms of v naught and sine theta, but we know that the horizontal distance we cover has to equal this. And this is where they would come up with some new variables. I swear sometimes it's just to confuse people. They would say the range equation. And the range equation is just how far you can go. So it's specifically looking at the maximum x value. And so we know that v naught cosine theta times how long you're in the air, but that's just this, is going to give us how far we can go. So then the range equation, this is just v naught, that's v naught squared, 2 cosine theta, sine theta, all over g. And if you remember some of your trig formulas, we do know that 2 cosine theta sine theta equals sine of 2 theta. And you can look at your angle identity stuff in trig class if you want to look where that came from. But that's a typical substitution to take this and rewrite it as sine of 2 theta. And so this range equation that you might see in a textbook is v naught squared sine 2 theta over g. And the best part is this is independent of time. This tells us how far we travel if we just know what planet we're on, how fast we were launched, and what angle. And so this, instead of being a position function of time, this is a position that's a function of velocity, angle, and g. And in this case, this also, if you investigate that a little bit, it does indicate that the optimal angle is 45 degrees. Again, if you have a certain canon and a certain planet and you want to maximize this value, that's making sine 2 theta the biggest. Sine 2 theta is the biggest at an angle of 45 degrees because that's sine of 90 and sine of 90 is 1, and that's the upper bound for a sine function. So what we've done here is we've derived the range equation for projectile motion. Now, as a reminder, this can only be used based on the assumptions we built it from. And if you remember, we built it using this. This is only true under symmetrical cases, meaning ground to ground. So this is only a symmetrical case. This, right, this is the range equation. Always true. I always can tell you how far you've traveled if you just tell me how fast you're traveling horizontally and how long you're in the air for. This is just nice because it doesn't have time. It can just tell us how far we can go based on the cannon speed and the angle we're pointing. Okay?